So, calculating for Qn, we can use the front minus back ay intuitive learning. Meaning, the higher enthalpy minus the smaller enthalpy of this system. So, here, so this is the 7. Again, sorry, there are follow-ups. So, great. So, finding the boiler's input and output. So, now, to find the total Qin, or Q input, is we find the total enthalpies of high minus enthalpy low of all heating. Meaning, we are going to include reheats. Therefore, Qin, so we now apply Qin is equal to 9, H9 minus H, what? If we're going to look at here, we can use H6 because this is 6. But 6 and 7 are just the same because of the reason, excuse me. So yeah, that's happening. H6 minus H7, sure, they're just the same. Therefore, even though they have this yields a lower enthalpy compared to H7 for some reason. But yeah, that happens all the time. H9 minus H7 times, what's this mass? Times 1 lang, times 1. So we need to also add the mass, which is 100 kilograms over there, minus, plus rather, sorry, the first reheat. So what's the first reheat? First reheat is at H12 minus H10, and the fraction is 1 minus mass 1. What's mass 1? 0.08, 0.097 times the mass of 100 kilograms plus H 14 minus H13 times 1 minus 0.097 minus 0.08 times 100. That's good. Plus, lastly is H16 minus H15 times 1 minus 0.097 minus 0.08 minus 0.11 times 100. That's our Schilling equation. With this now, we are just, I'm not going to plot it in, so we're just going to plot it in our calculus directly. So now, follow me. 3582.3 minus H7 is, H7 is equal to H6 plus minus close enough to H6. 864.99, therefore times 100 plus H12, but H12, 3674.4 minus H10 is 3153.25 times 1 minus 0.097 times 100 plus H14 is 3694.9, again wait, 3694.9, 0.4 rather, minus H13, which is 3325.20, times 1 minus 0.097 minus 0.08 times 100. Plus, lastly, is H16, which is 3702.4, 3702.4 minus 3231.90, which is our H15. Then 1 minus 0.097 minus 0.08 minus 0.112 times 100. So now we yielded a really big answer of 382,628.55 kilojoules. Why kilojoules? Is because we did not account for its time. Oh yeah, it's kilojoules. That's really big Qn. Why kilojoules? Why not kilojoules per kilogram? So why? Because we added the mass here. Therefore, the over kilogram is eliminated. Therefore, it's just kilojoule. Or we can just simplify it to 382 megawatts. So that's really high input. A very big number. So now we can now find for the Qout. So Qout now is just simply H1 minus H17, or reverse. H17 minus H1. Either way, they're just going to yield the same. 1 minus 0.097 minus 0.08 minus 0.112 times 100 kilograms. So now, Qout is equal to H17. What's H17? 3220.51 minus 1 is 191.83. After that, we multiply it. 1 minus 0.097 minus 0.08 minus 0.112 times 100. Therefore, our Qout is also very big, which is 215,339.15 kilojoules, or 0.339 megajoules. It's megajoules. So we have Qin and Qout. Now, because all of this is an ideal system, we can directly solve for its efficiency using Qin and Qout, or we can also solve its network output. Either way, we can solve network output by using this 9 minus 10, 12 minus 13, 19 minus 5, 15, 14, 15, 16 minus 17, with applying this ratio so we know. But also because everything is ideal, meaning we can use the formula of the efficiency or the work net, which is equal to Q input minus Q output. Therefore, our input in megajoules is 382 minus 215. To simplify things, so 382 minus 215 yielded a really small or really bad number for some reason. Megajoules. So that is our network output. To find the efficiency now, efficiency is equal to 1 minus Q out over Q in. Or since we got that, we can also use work net over Q in. Either way, they are going to yield the same answer. So now if you're going to use the bottom one, 1 minus 382 over 215, or we can use 167 over 300, sorry. Oh no. My bad. So at the upper part, we are going to use 215 rather. Then this is 382. This is 382. And this is 167. This efficiency will always lead to the same answer because they are just the same formula. 382 it has an efficiency of 0.4372. Using the other formula, we will also yield 167 divided by 382, which yielded also the same amount. Therefore, this is the efficiency of the cycle that we made. With those efficiencies, those are really high compared to a normal one. But what happens here is that its efficiency increases, but when you're building a power plant, the power plant is really expensive due to its many peripherals, such as the open feed water heater and the closed feed water heaters and reheats and whatnot. More materials means more cost, but it would also yield to higher efficiencies, which would be, we need to study that so that you can make a really good power plant. So yeah, this is how you solve for it. Take note that you can also get Wnet by doing work pump total plus the work of this individual total. It will still yield the same amount, 167 megajoules. Now, in the question, it says per kilowatts. But what happens here that I missed the part is where there is an S. So this is my bad. So this is now, that's a flow rate, megawatts. So yeah, it's megawatts. I thought there is just only 100 kilograms. So that's a mass flow rate. So yeah, that's everything.